In this video, we're going to begin discussing vector functions. In previous videos, we've looked at vector notation and operations, and now we're going to begin using them to extend the concepts of calculus through three-dimensional space. Our focus initially is going to be on curves in three-dimensional space, and so we're going to be able to represent those curves by vector functions, and I'll explain what a vector function is in a moment. And later on, we're going to be doing multivariable functions as well, but for now, we're going to focus on vector functions. So to define a vector function, we're going to start by letting capital D be a set of real numbers. Now this can be any set, but almost always it's going to be an interval. So I'm just going to put parenthetically that we want to think of D as an interval. So maybe all the real numbers from 0 to 5, including 0 and 5. Something like that. So a vector function vector function defined on D is going to be the domain of that function, is just a function that assigns a vector to each number in D. Right, so if D is an interval of real numbers, then each of those real numbers is assigned some vector in 3 space or in 2 space. This could be a 2-dimensional vector function as well. And in terms of notation, what we will often do is maybe we'll call this function R. So it'll be R of t. Notice we've called R a vector by indicating the arrow above it. And we can write this using either the standard basis vectors. So we could write this as f of t times I plus g of t times j plus h of t times k. And we could also write this in component form as the vector f of t, g of t, h of t. Right? And in either of these cases, we want t to range over all of the set D. And if D is an interval, then we want t to range from the left endpoint of the interval up to the right endpoint. These three functions, f, g, and h, notice these are not vectors. These are scalar functions. The output is a scalar. And these are called the component functions of R. Okay. So R is the vector function. It outputs vectors for each input. And these three component functions are just your normal functions that you've studied since algebra. You input a real number and you output a real number. Right? And so these are the three component functions for the vector function R. One last thing to mention about vector functions is that the output of these are vectors, but the way that we're going to view them is as position vectors. And that is, whenever we output a certain vector, we're going to think of the vector starting at the origin and considering the terminal point of that vector. And so in this sense, this vector function will take every number in the interval D and will output a point in 3 space. And if we think of t as time, as t goes through D from the smallest value to the largest value, we get a point that actually will travel through space, and we can consider that path of that object. And that's how we're really going to want to think of vector functions in the context of calculus. Okay, so let's look at an example. So let's consider the vector function R of t defined by the component functions cosine t, sine t, and t. Right? And this always has to come with some interval. So let's say we want to define this with t in the interval from negative 2 pi to positive 2 pi. Right? So in the sense that for every real number between negative 2 pi and 2 pi, r of t outputs a vector given by cosine of t, sine of t, and t. And then that vector identifies a point in 3 space, specifically the terminal point of the vector when it's in standard position. So if we want to try to figure out what this space curve looks like, we can just analyze some certain components of this particular function. So for example, if I focus on the first two components, the x and the y component, I know that cosine squared of t plus sine squared of t is equal to 1. It's one of the first things you will learn about sine and cosine in trigonometry. And so that means that every point identified by this vector function, every point on this space curve, is going to satisfy x squared plus y squared equals 1. And we know that this is a cylinder. Right? It's a cylinder that you form by taking the unit circle in the xy plane and raising it up and down indefinitely along the z-axis. So we have this big cylinder. So every point is on this particular cylinder. And so the third coordinate, z equals t, what this tells us is that as z increases, the vector r of t is going to travel, I'm going to use this word in quotes but you know what I mean. It's not really a great word to use, but the function the vector r of t is going to travel up the cylinder. So as t increases, another word of saying this is that as t increases, so does the vertical position. And so here is an image of this particular space curve. So you'll notice in here we have the x and y axis making the flat plane. The z-axis is pointing upward, the standard right-hand coordinate system. The blue surface here is the cylinder. And you can see that if you look down from the z-axis down towards the xy plane, this would make the unit circle in the xy plane. So it's the cylinder x squared plus y squared equals 1. And then the red curve is actually on the outside of this cylinder, and it curves upward. It's a little bit hard to see in this image, but there are some arrows here that are indicating that the curve is going upward. So down at the bottom, you can see when z is negative 2 pi, that is our starting point for the curve. The curve goes up, around, and then ends up at the top when z is equal to 2 pi. And that is our interval, t going from negative 2 pi to 2 pi. And so we can really think of this as a sort of an object moving from the point at the bottom of the cylinder to the point at the top, and that at each time t between negative 2 pi and 2 pi, the vector function is identifying the position of that object at time t. So now looking at this kind of a scenario where we have a vector function defined on an interval and we can represent it with a space curve, we can see how we can perform calculus in scenarios like this. For example, if t is approaching a number like 0, we might ask the question of what position in 3 space the object is approaching. Right? This is a limit problem. We might also ask at a particular point in time, say when t is equal to pi over 3, how fast and in which direction is the object moving? Right? And this is a derivative question. Right? So we can bring in all of those techniques that we've learned in calculus before, limits, continuity, derivatives, integrals, in order to answer analogous questions about space curves in 3 space given by vector functions. So I've used the term space curve a few times in the previous slides, so I want to take a moment and just give this a a formal definition. Right? So if we're given continuous functions f of t, g of t, and h of t, defined on some domain D, then the set capital C of points traced out by the vector function r of t, which is going to have component functions f of t, g of t, and h of t, where t ranges over d, is called a space curve. So a space curve is simply the set of points traced out by a vector function as t ranges over the domain of that vector function. The only caveat is that the component functions have to be continuous, right? And that's continuous in the calculus 1 sense, since f, g, and h are not vector functions, but rather scalar functions. We saw in the previous example, if we have a vector function, like r of t equals cosine t, sine t, t, we saw how we could use our knowledge of three-dimensional geometry to sketch out the space curve. In particular, in that example, we got a helix that lived on the cylinder x squared plus y squared equals 1. Another thing that we will sometimes have to do is take a curve in space and come up with a vector function that describes it. So for example, let's say I'm going to define capital C to be the intersection of the cylinder x squared plus y squared equals 4 and the plane x plus z equals 2. Right, so I have this particular space curve, and you can see what this is going to be. This is going to be some kind of a conic section because we have a cylinder and we're cutting it by a plane that's going to cut in at an angle. So we're going to get some, it's not going to be a circle, but it's going to be an ellipse or something like this. And what we want to do in this example is to describe this curve C as a vector function r. So in other words, we want to write down a vector function r and a domain D for that vector function that will trace out this curve as t ranges over that domain. Right, so in order to do this, in any kind of example like this, we need to introduce a parameter t. And that's because to get the vector function, we need this t. And so we can do this in any number of ways. In my approach, I'm going to start with the cylinder. All right, so I'm going to start with that cylinder, x squared plus y squared equals 4. And I'm going to introduce the parameter in terms of that curve, in terms of that cylinder. So I might let x be 2 cosine of t and y 2 sine of t, and t ranging over the interval from 0 to 2 pi. Right, this would describe x squared plus y squared equals 4, along with the z coordinate being whatever we want. All right, we can see here that if I take x and y that I've defined, if I take x squared plus y squared, I will get 4, and I will get the entire cylinder by going from 0 to 2 pi. And now, if we introduce the plane, I know that x plus z equals 2 is the equation of our plane. Right? And so from that, I can see that z is going to be 2 minus x just by rearranging. And so if x is 2 cosine t, that means z must be 2 minus 2 cosine t. Okay. And now I have all three of our variables in terms of t. And so these will be the components of our vector function. So the vector function that gives this particular curve is r of t equals 2 cosine t, 2 sine t, and 2 minus 2 cosine t. And we want t, in this case, to range over the interval 0 to 2 pi. Right? So this is one example of a vector function in a domain that describes our curve C. It's certainly not the only one. When I picked my parameterization for the cylinder, I could have picked x to be 2 sine of t and y to be 2 cosine of t. And that would cause z to actually be 2 minus 2 sine of t. Right? I also picked t to go from 0 to 2 pi. That's the most natural interval. But of course, you could take t to range over any interval which has length 2 pi. And so there's lots of different options for this. But this is probably one of the more straightforward ones that you can find.